All right, everyone. Sorry this one is a little late. I'm sure you guys are devastated about it. Anyway, let's get right into it. This unit is over bonding, and in my opinion, one of our most important units. So we have a few little definition type things here. First off, a bond is a force that holds atoms together. It takes two electrons to make a bond, by the way. More on that later. There are two types of bonds here, ionic and covalent. For ionic bonds, there is a transfer of electrons, and for covalent bonds, there is a sharing of electrons. Now, some of this will be review for you guys, so I want to go through it a little faster than normal. So, all of bonding actually has to do with this idea of electronegativity we talked about in our last unit. As we already said, electronegativity is a measure of the ability of an atom to attract electrons to itself. And this guy, Linus Pauling, came up with this scale of electronegativities, which you have seen before. Now, there are two types of covalent bonds, polar and nonpolar. And the way we tell the difference is through these electronegativities. What we do is when we're bonding two atoms together, we subtract their electronegativities, and this difference will tell us whether it is between 0.3 and 1.7 or not. If it is in that range, we categorize the bond as polar covalent. If it is less than that range, we call it nonpolar, and if it is more than 1.7, that makes it an ionic bond. We should discuss what it means to say something is polar or nonpolar. Here in this example, we have HF. H is less electronegative than F. What this means is that the fluorine will pull the electrons closer to it. You can think of it as if hydrogen and fluorine are playing like tug of war with the two electrons between them, and fluorine pulls harder. Like they're sharing the electrons, but they're not sharing them equally, if that makes sense. This gives hydrogen a partial positive charge and fluorine a partial negative charge. And the fact that it has these two partial charges is what gives it a dipole, or two poles, meaning it is polar. All right, so let's briefly talk about these forces going on inside the bond. Basically, there is a balance of attraction and repulsion. We have obvious attraction between the nucleus of one atom and the electrons of the other atom, but this is actually balanced out by the repulsion of the electrons with the other electrons. Like the negative charges don't want to get too close to each other, right? The same with the two nuclei. So there's actually a distance that these things are stable at. And if they're brought too close together or too far apart, it just doesn't work. Here you can actually see a picture of this going on. In the top left here, we have two hydrogen atoms that are close together, but too far apart to interact, so there's no bond. A little closer together, there starts to be an interaction, and by the time they get this close together, there's an actual bond formed between them. You can also see this depicted in this graph, where just like right here, they're too far apart, would be all the way to the right, where they're too far apart here. The bond energy is zero because there is basically no bond between them. And as we bring them closer together, we reach a bottom point in this graph. This is the distance the hydrogen atoms need to be in order to be most stable. All right, so we're talking about these bonds, and we can measure more than just distance, we can measure the energy as well. What we're actually talking about is the energy it takes to break the bond, and this is the way we measure the bond's strength. So if it takes more energy to break, that means it's a stronger bond. Each of these lines represents a bond between these atoms, meaning each line represents two electrons. So we can actually compare the strength of these bonds. This is telling us that a carbon-carbon double bond, two lines means two bonds, takes 614 kilojoules to break, while a triple bond between carbons is 839 kilojoules. That means it's stronger. A carbon double bonded with oxygen is somewhere in between at 745 kilojoules, and a carbon-oxygen triple bond is much stronger at 1072 kilojoules. All right, a very important topic in this unit here is Lewis dot models. You should have seen this in 9th grade, but again, I don't necessarily expect you to remember that. If you do, it just gives you an advantage. These are used to give you an idea of how many bonds are formed when the atoms react, as well as the charge of the ion when the atom reacts. So this is an example of oxygen's Lewis dot model. The inner electrons and nucleus are all modeled with the chemical symbol for oxygen, or the O in the middle. The outer electrons are represented by dots around the O. Oxygen has 6 valence electrons, the outer electrons, so we draw these as 6 dots around it. There are 4 sides to the Lewis dot model, and each side can only hold 2 electrons. That means that the maximum is 8 electrons. And we know exactly how many valence electrons every element has just by looking at the periodic table. Any element in group 1 will have 1 valence electron. Any element in group 2 will have 2 valence electrons. Any element in group 13 will have 3 valence electrons. Any element in group 14 will have 4 valence electrons. Group 15 has 5 valence electrons. Group 16 has 6 valence electrons. Group 17 has 7 valence electrons. And group 18 has 8 valence electrons, except for helium, which only has 2 total electrons. All right, so we have a couple rules for these Lewis dot models and how you fill these out. Step 1, know how many valence electrons the atom has. Step 2, fill in 1 valence electron per side until all sides have 1 before pairing them up. Step 3, you can start on any side and go in any direction, but there is an actual convention for this. I always start on top and go clockwise to the right side around. And again, make sure you don't double up until each side has 1. That's it. It's not too complicated. Okay, so these Lewis dot models can actually have a lot of information, but you need to know that these unpaired electrons are the bonding electrons, or if you prefer, they are single and looking to mingle. The already paired electrons are not involved in bonding. They already found their mate. Anyway, this tells you that oxygen has 2 open spots available for bonds with other atoms, because this electron is single and this electron is single. So, this means it could form a bond with 2 hydrogen atoms, like in H2O, or it could form a double bond with something like carbon, like in CO2. Or, in an ionic bond, oxygen would want to gain 2 electrons to make 8 valence electrons, and this would put the charge at 2-. Yes, there's a VIP on this, so you don't have to memorize it. This one gives you just the example of row 2 elements as Lewis dot models. Lithium has 1 valence electron, so there's 1 dot. Boron has 3 valence electrons, so there's 3 dots. 1 on each of 3 sides. We don't start doubling up these electrons until we get to nitrogen that has 5 valence electrons. Again, here's oxygen with 6, and neon here has 8 valence electrons. Again, this is just showing you in another way that these noble gases are unreactive and do not like to bond with other atoms. Okay, so yeah, we've talked about this octet rule before a little bit, right? If you don't remember, it's basically that every atom wants to fulfill their one ambition in this life, which is to find a way to get 8 valence electrons. They'll give up their electrons or share their electrons with other atoms. They'll do whatever they can because this is how they become most stable. So you can see these are all 9 electrons in the fluorine atom, and these are where they're located in these orbitals. The 1s electrons are inner, and the 2s and 2p electrons are the valence electrons. That's how we get 7 valence electrons. And when 2 fluorine atoms bond together, they are sharing their 7th electron with each other. These 2 electrons make a bond between them, and they both have claim to these electrons. This gives both atoms of fluorine 8 valence electrons. This is that exact thing working with a bond between hydrogen and chlorine, just to show you where the electrons are that are bonding. The only electron chlorine has to bond is in the 3p orbital, and hydrogen's is in the 1s orbital. They share these and both have a full outer shell, chlorine with 8, hydrogen with 2. This is another picture to show a reaction going on with these Lewis dot diagrams. On the left, we have 2 hydrogen molecules, an H2 and another H2. The 2 dots between them represent the bond, and we have a molecule of O2. 2 oxygen atoms double bonded together. Again, each bond is 2 electrons, so when it shows 4 electrons between the oxygens, this indicates a double bond between them. And on the right side, we are making water. Just like I said earlier, each oxygen has 2 spots where it can react with something and bond. In the middle, this means that the 2 open electrons are bonded with the 2 open electrons in another oxygen atom. But on the right side, the oxygens are bonded with 1 hydrogen at each of these 2 open electron spots. Now, there are some exceptions to this octet rule, and we will try to avoid them honestly. Just know there are certain elements like boron and beryllium that are so reactive they can actually have fewer than 8 electrons around it. And there are other elements that could have more than 8, but again, we will try to avoid these rare exceptions. Okay, so now we can move into actual molecules. Like Lewis dots are great, but they only show like 1 atom at a time. Let's get a little more complex here. These are able to show the valence electrons of multiple atoms at once, as well as reinforce this octet rule that each atom is much more stable with a noble gas conformation. So there are some steps to this, and we will use this CH3Cl as an example. Now, if carbon has 4 valence electrons, and they're arranged like this with 1 on each side, this means that it will form 4 bonds. This is great because we have 4 things to bond to it. You're going to make carbon the central atom, so you put it in the middle, and then you're going to put the other atoms around it. It doesn't matter which one you put first. You should add up all of the valence electrons from each atom, so you make sure you put the correct number of dots for the whole molecule. Carbon gives us 4, each hydrogen comes with 1, and since we have 3 of them, that gives us 3 more valence electrons. And finally, chlorine has 7. So adding all of these together gives us 14. So we better make sure to have 14 dots in our answer. The next step is to connect these atoms to the central atom. Remember, each bond is 2 electrons. Now we need to remember that chlorine came with 3 pairs of non-bonding electrons, so we have to show those here as well. And as long as every atom has their valence shell full, and we have the correct number of valence electrons used, then we're good. Okay, so we sort of covered this earlier. There can also be a double bond between atoms, and that is represented with either 2 dashes or 4 dots, same thing. C2H4 is an example of this, and C2H2 is an example of a triple bond formed between the 2 carbons. Okay, I just want to show you how this kind of happens. So at first you'll start with the Lewis dots of each of the atoms we have, 2 carbons, 2 hydrogens. Then we are going to connect the 2 carbons together with those 2 single electrons. Then we're going to connect the hydrogens to the carbon by pairing those electrons. Now we have those represented as bonds with lines. Now we have all of the atoms connected, but you'll notice something is strange here. We don't have non-bonding pairs of electrons on carbons. We have bonding electrons that are single and looking to mingle. So what they're going to do is find each other and create bonds like that. That's how we get this triple bond between the carbons. There's also this idea of resonance structures. Basically, you could see this as rotating the molecule and it would be identical. Like the top left carbon is single bonded to a carbon and then double bonded to another carbon. And the top left carbon over here is also single bonded to a carbon and double bonded to another carbon. Like these are representing the same molecule. They both have 6 carbons and 6 hydrogens, but these are slightly different representations of it. Here's an example of resonance structure for ozone. It's still 3 oxygens bonded together in a line, but does the double bond go on the left side or the right side? This is just 2 different ways to draw it, and the real molecule exists as kind of an average between them. A couple more examples of resonance here. You can see the double bond is going to the top oxygen in this one, the left oxygen in this one, and the right oxygen in this one. Again, if we can move the double bond to a different spot, basically that makes it a resonance structure. Last topic here, we can show these Lewis diagrams with ionic compounds too. Basically, for ionic compounds, the more electronegative atom steals the electrons from the other atom. Remember that tug of war example? Well, it's basically like the more electronegative is so strong, it pulled the whole rope away from the other atom. Anyway, here you can represent them with X's for the cations, but it's not mandatory, just showing you that they can be. So this is showing you that how that would work with forming a water molecule. As you can see, these X electrons from the hydrogens are being bonded with the open electrons in oxygen to form water. Alrighty, this is our example of ionic bonding. Remember, sodium has 1 valence electron, and when it reacts, it is going to be charged as +1. It gets that way because it transfers its electron in the reaction. For this example, it transfers to chlorine, and this is also how chlorine gets to be -1, because it now has an extra electron. And as you can see on the right side of the reaction, both elements have now fulfilled their life ambition to have 8 valence electrons. You can also tell how many atoms you need for the chemical formula by seeing how the Lewis dot models will interact. For example, if you were told to come up with a chemical formula when magnesium reacts with fluorine, you would start out by drawing the Lewis dots for both elements. Then you would notice that magnesium has 2 electrons to give, but fluorine can only take 1 electron before it's full. What that means is that you need another fluorine atom for magnesium to react with. This is where it donates its second electron to that second atom of fluorine. Now that we reacted magnesium with 2 fluorines, every atom has a full valence shell because both fluorines have 8, and since magnesium got rid of its 2 electrons, its inner electrons now make the full valence. Along the same lines, we can react lithium with oxygen. We would start with a Lewis dot diagram of both elements. And since we have an oxygen with 6 valence electrons trying to get to 8, we would then need to react this with 2 atoms of lithium, each giving up 1 electron for oxygen to make 8. And since they only had 1 valence electron, getting rid of it actually makes their inner electrons count as the full valence shell now. Alright guys, that is actually the end of the notes for this unit. I know this was a long one, and I'm sorry, but that's why it took me a little longer for the video. Now you guys know the drill by now. There will be a couple Schoology assignments and just a couple more Google Meets before we're on break for the holidays. As always, thanks for watching.